See my screen?
Yes, we can see your screen. We can also hear you.
Okay.
Okay, great. So welcome to the last talk of this morning session. I'm sorry if we're a bit behind schedule, but I think that's fine. So we have now a talk by Marica Minucci from the Queen Mary University of London. And someone is typing, so someone needs to please mute himself or herself. Not sure who that was.
Sorry, that was me.
Oh, never. Okay, great. So again, we have a talk by Marica Minucci from Queen Mary, and the topic is stability of Einstein spaces with spatial sections of negative scalar curvature. Welcome to the seminar.
So first of all, thank you to the organizer for inviting me to speak today. My talk is a work about existence, which is stability for the solution to the vacuum Einstein field equation with positive cosmological constant. This kind of space-time, which has been widely studied. One paper, for example, is the one of Fajiman and Kroenke about the stable fixed point for the Einstein flow with positive cosmological constant. But the aim of this work is mainly to show that it's possible to get this result by means of conformal method. In particular, what we do is to consider the space-time mg, where G is a metric such that the trimetric gamma ring is a positive definite metric with constant negative scalar curvature. So the first thing that we do is to try to then embed this space-time that we will refer from now on as the physical space-time into a cylinder whose section has negative scalar curvature. We do this by means of conformal geodesics. For people who are not familiar with conformal geodesics on this physical space-time are a pair of x in one form beta that satisfy the following equation, which are the conformal geodesic equation. Now, to recast our matrix geodesics on this physical space-time as a conformal geodesic, we consider a parameterization of this form. Then we use this tau also as a new coordinate for the metric G, which is, as I said, is the physical metric. And then by means of a conformal transformation, we have the unphysical metric G ring, which is a metric which is well defined for tau that goes from a certain tau star to infinity. So we realized a conformal bending of this the zeta-like space-time by means of a conformal factor theta, which is proportional to tau, which is also a time coordinate for our metric. So what we do is to then formulate the conformal Einstein field equation. In this case, what we do is not to consider the conformal Einstein field equation, but to consider the extended conformal Einstein field equation. These extended conformal Einstein field equations are equations which are conformal equation, but they are formulated in terms of the Weyl connection, which is a non-metric torsion-free connection. And the reason behind this is that the use of conformal geodesics together with this Weyl connection, and so with this kind of conformal equation, led us to have somehow a natural conformal factor out of the conformal class. So we formulate the frame version of these equations by defining these following quantities. So this equation turns out to be conditions on these quantities. But we have also other quantities, which are the fields theta and d, which is defined in terms of this Weyl connection. And they are regarded as conformal gauge field, and they are determined by supplementary conditions. The supplementary conditions are given by the definition of other some of zero quantities, which are delta, gamma, and bar phi. So the first step in the study of this equation is to study before the conformal constraint equation. we solve this conformal constraint equation on a three-dimensional manifold S, which is a space-like hypersurface on the unphysical space-time. And to do this, what we do is to use adapted coordinates, so an adapted frame. And the result that we get, we will consider the following, and we will consider this result as our initial data in what follows. So we move to the study of the evolution equation. We have two evolution systems. The main evolution system consists of an evolution equation for the frame component, the connection coefficients, the rescale by tensor, and the components of the Schouten tensor, and they're obtained by the following condition. We have also an equation for the evolution equation for the covector that defines the Weil connections from the Levi-Civita connection. But we have also another evolution system, which is the subsidiary evolution system. And we get system once we know that the main evolution equation are satisfied, and then we have supplementary conditions, evolution equation for the additional zero quantities, which are delta, gamma, bar phi. So what we've done is to study in order this main evolution system. By the study of the system, what we found out is that all the evolution equation that we get can be recast as a system of equation for quantities b and phi, which are defined in these terms. But this system can be expressed in turn as a symmetric hyperbolic system by means of definition of U. Also, what we do is to use a sort of perturbative approach in which we consider the solution to the equation U has given by the sum of U ring, which is regarded as the exact, the sitter-like solution expressed in terms of these conformal Gaussian coordinates, plus U check, which is a small perturbation. So since on the initial hypersurface, we have that U ring star is following, so the equation are automatically satisfied, we get by this approach an equation for a system for the perturbation U check. Then what we've done is to study this equation, and then we have a proposition for the existence and stability of the sitter-like solution to the extended conformal evolution equation. What we've done is then the statement says that then if we U check star is a small perturbation of the de Sitter-like initial data of the conformal field equation prescribed on S, which are the following, we have that there existed Sobolev norm of this initial data is bounded by epsilon. And then if this holds, we have that then there is unique solution U check in this space. And also we have that if U ring star belongs to an D, which is a bounded open subset of the Sobolev space H to the K, then we have that there is a common initial time, existent time to all the initial condition in a small neighborhood of this given point inside the ball. And eventually we have that if we have a sequence of initial data U check such that the Sobolev norm of this initial data converges to 0, then we have that even the Sobolev norm of the solution U check had converge for tau in this set as n goes to infinity. But how do we prove this? The first step is to consider the manifold itself. The dimensional manifold is compact and smooth. Because of compactness, what we do is to then cover this manifold by a finite number of sets, and we associate to every set local coordinates. Then since this manifold is also smooth, we have that the change of coordinate in the overlapping domain is smooth. Second, we have, if we have this U check defined on S, we have that this U check can be restricted to a particular open subset in our I. Then we can extend this restriction to a function from R3 to Rn and define the Sobolev norm of U check star in the following manner. So once we've done this, we move to consider the initial value problem for the Cauchy problem for this quasi-linear symmetric hyperbolic system. And then since the matrix A turned out to be positive definite and the B are at most quadratic in their dependence, what we have is that all the conditions to Cato theorem are satisfied. So Cato theorem then gives us existence, Cauchy stability, uniqueness result for our initial value problem. But then this also for all these small balls that covers our manifold. To extend this to the old manifold, we consider the fact that since we have in every ball we have a solution, what happens here is that because of Cato, on the overlapping domain, we have two solutions, they must coincide. So by extending this procedure to all the intersection and to all the patches, what we have is that then the initial value problem is satisfied. And we have, again, Cato existence, uniqueness, and Cauchy stability result. In particular, what we have is that then there is a common existence interval for all the solution in this space. We have that then if this epsilon is measured in 0, and then this tau bullet is common, is chosen for all the initial condition on the open ball, we have this ball inside D. And then we have also that the solution you check with this initial data, you check star exists in this set, we have that all the solution to all the initial condition exist in this set for epsilon sufficiently small. And then as a result, we have that then if epsilon and this tau bullet are chosen as in B, we have that then we have convergence result for the Sobolev norm of this sequence. And so this is the main result for the main evolution system. But then, as I said, we have another system, which is the subsidiary evolution system. And then as we've seen, since the main evolution system equations hold, we have the subsidiary evolution system, our equation for the following quantities. This equation can be in turn expressed as a symmetric hyperbolic system by defining this overall quantity capital X. And the symmetric hyperbolic system is also such that it's homogeneous in the 0 quantities. And even here, with the same procedure that we used for the previous symmetric hyperbolic system in its corresponding initial value problem, we have that then, by the same reasoning, we can prove that Cato theorem holds. And then since the initial condition is such that all the 0 quantities vanish on 0, they vanish in all the set. And then by this, what we have is that if you had star is the solution to the conformal evolution equation such that this conformal equation is satisfied, we have then the proof of a statement about the propagation of the constraint. That tells us that if this equation holds on the prescribed manifold S, we have that then this implies in turn a solution to U hat for U hat to the extended conformalized self-field equation. So then for what we've seen up to now, the solution to the evolution equation together with the conformal constraint equation, a solution to the conformal constraint equation gives us a solution to the extended conformal I self-field equation. But at the very beginning, we thought about the de Sitter-like space-time. So how do we recover, what is the correspondence between a solution to the extended conformal I self-field equation and our initial space-time? This correspondence is given by the following proposition. So if this set is a solution to the extended conformal I self-field equation for some choices of this gauge field, which in turn satisfies some supplementary condition, and then we suppose that these conditions hold on an open subset U, then we have that this metric is in turn a solution to the vacuum I self-field equation with cosmological constant on the subset U. So in conclusion, we've shown that then these two solution of the nonlinear perturbation equation together with solution to the constraint equation gives us a solution to the extended conformal field equation. And then in turn, we have a solution to the Einstein field equation. So we've seen how a method that is based on conformal equation together with a gauge adapted to the frame and the conformal geodesics, we have existence and stability result for the Einstein field equation. So thank you for listening.
Okay, thanks a lot for this nice talk. Are there questions from the audience? I always have to orient, so do I see?
Yeah, so may I ask a question? So
Yeah.
Your theorem sounds a bit like a theorem that Helmut proved years ago, but he used it. So the difference is that you're using different differentiability conditions and different setting. Is it, do I understand correctly, or?
What we've done is to, as I said, this kind of problem related to the capacitor-like it's a nice space-time with positive cosmological constants are widely studied in many ways and even with conformal method. But what we want to prove is that by keeping the trimetric completely general, by just requiring that is as negative scalar curvature, we can still get existence, Cauchy stability result for our initial space-time.
I see. So this generalizes Helmut's theorem, who took just plain de Sitter, while you can do this for a more general class of metrics. And also, I mean, in his original version, he didn't use the conformal geodesics and stuff like that. He used the previous formulation, but okay.
Yeah, and also it's very nice because then, since we have an adapter frame, then by means of the byte connection, since the frame is byte propagated along the geodesics, we have the solution, the evolution follows literally follows the geodesics.
Okay, thank you very much. Thanks.
So are there further questions? Okay, well, if not, then thanks again for this nice talk. And thanks everyone who gave a talk in this session.